Good afternoon, everyone. I hope your week is going well. We are going to start today's lab, so we are now recording this session. So today we are doing the equilibrium constant lab. So the objective of this experiment is to determine the most likely equilibrium constant and stoichiometry of an unknown metal ligand complex using the ICE method and Beer's law. So a few weeks ago, or last week, I think we did Beer's law. So we are going to be using A equals EBC again this week. And we are also going to be using M1V1 equals M2V2 and some simple algebra to figure this out. Okay, so today's concepts. So equilibrium. Equilibrium of a chemical reaction is reached when relative amounts of products and reactants stays the same over time. So what this means is the reaction does not stop, but that the forward and reverse reactions are proceeding at the same rate. So a few days ago, we did the kinetics experiment. So if you can imagine that the forward and reverse reactions have the same order and they're going at the same rate. And so when we have specifically reactions in solution that don't form like solid products, we can reach an equilibrium. And so reactions that reach equilibrium are written with a double-sided arrow, and that shows that the reaction is moving in the forward and reverse direction at the same time. Okay, so reactions that reach equilibrium are different than reactions that go to completion. So like the iodine clock experiment where we were forming a product that was a gas that escaped, that reaction would keep going because due to Le Chatelier's principle, when I2 is escaping into the fume hood, the reaction would be continuously producing I2 gas. However, in this reaction, we are reaching an equilibrium, which means it's reversible. So reactions that go to completion are irreversible reactions because you can't get that product back and you can't reform the original reactants. And those that reach equilibrium are called reversible reactions. And so there's this little symbol here. Okay, so reactions that reach an equilibrium have an equilibrium constant. So depending on what the concentrations are, we can figure out what that equilibrium constant is. So the equilibrium constant is defined as a ratio of products to reagents at equilibrium. So the equilibrium constant describes the concentration of everything at equilibrium. So in a chemical reaction, the equation of the reaction always has this form where we have one reactant plus another reactant makes a product. Or it could be the other way around where a reactant dissociates into two products. It doesn't really matter. But the capital letters A, B, and C denote the chemicals. And then we also always have to balance our chemical equations. So we put coefficients in front of the molecules to balance that equation. And so the coefficients in front of the chemical, when we write our equilibrium constant, those are going to become powers. So in the equilibrium constant, it's defined as the concentration of the products to the power of that coefficient divided by the product of the concentration of the reactants to their coefficient powers. Okay. So how does that compare to what we are doing today? So we are exploring some metal complex bonding. So metals, so those things that specifically like transition metals, they can have expanded octets and they can bind covalently or non-covalently. So think of it more as like an interaction between ligands. And they can do this in multiple ways. They can fill their octet, they can expand their octet. So it's not always simple to predict whether a metal is going to bond one or more ligands. So in today's experiment, we are assuming that the metal M will bond to either one or two ligands. So for us, that means the stoichiometry of the product is either ML or ML2. I'm going to bring up a whiteboard real quick. And whiteboard. All right, so that means our reaction is going to be M plus, oh, hold on. Okay, so our reaction, if it's ML, it's going to be M plus L minus gives ML. Or if we are making ML2, it's going to be M plus 2L minus makes ML2. Okay, so the different stoichiometry is based on whether we have one ligand or two ligands binding. And so this is important because that means our K is going to be different. So our K for the ML would be K equals the concentration of ML over the concentration of M plus times the concentration of L minus. Right, that's pretty straightforward. But what about the ML2? So K for that is going to be the concentration of ML2. Remember, this is all at equilibrium. Over the concentration of M plus. So you can think of this as having 1 in front of it. But the L minus, we have to square that concentration. So the difference is going to be here. Okay, so let's go back to the slideshow. Okay, so how are we going to figure this out? So we are going to start with known initial concentrations of M and L. And so to begin with, we have a certain concentration of M and a certain concentration of L in different containers. Yes, K is the equilibrium constant. So we have M and L, and because we haven't started the reaction, we don't have any ML complex to start with. And then the reaction, once we mix those two together, it's going to occur, it's going to keep going until it reaches equilibrium. And then we are going to have some ML complex created. And the amount of ML complex created for hypothesis 1, or 1M plus 1L makes ML. The amount of ML created is going to equal the amount of L that was used to make ML and the amount of M that was used to make ML, because we have a 1-to-1-to-1 ratio. So if we gained a certain amount of ML, we're adding ML to the concentration of ML. And that means we have to subtract that concentration from our initial concentrations of M and L. And so at equilibrium, the concentration of M is going to be the initial concentration that we had of the metal minus the amount we used, or the amount of ML that we made, to find the concentration of M at equilibrium. The same thing for L. So we started with an initial amount, we're subtracting the amount we used to make ML, and we're left with the amount left over of L at equilibrium. Okay. So once we have the equilibrium values, we can figure out what K1 is. All right, but what about the second hypothesis? So how is that different? It's going to be different in two ways. So in our ICE table here in the initial change equilibrium, so the ICE table, we have to remember that we're using twice the amount of L as we are M. So, and we're making ML2. So in this ICE table, there should be little 2s where the L is. I know that is a little bit confusing here. So we start again with the initial concentrations of M and L. And to start, we don't have any ML. So then we are going to be making a certain amount of ML, which will be measured, and we'll talk about that later. So we're using one equivalent of M to make ML, right? So 1-to-1 ratio. So the amount of ML we make is the same amount of M that we are using. So the M initial minus the ML at equilibrium will give us how much M is left over at equilibrium. However, for L, because we're using twice the amount of L as we are M, that means we're losing twice as much of L. So L minus 2 equivalents of the ML complex at equilibrium will equal the amount of L we have left over. So in this case, this number should be smaller than hypothesis 1. Okay. So the second thing that's going to be different is, again, in K2, so for the K value, the equilibrium constant for this second hypothesis, when we do that calculation, we have to make sure that we are squaring the concentration of L at equilibrium. So the value that we get here in our ICE table, we will put that to the power of 2 before we multiply it by this value here of M at equilibrium. Okay, so how are we doing this experimentally? So we are going to use Beer's law. So the metal complex is going to be like a reddish orange color. And that means that it absorbs bluish green light. and the wavelength of bluish green light is going to be 460 nanometers. So we are setting up our spectrophotometer at 460 nanometers. So again, we want to read absorbance and not transmittance. So we went over that in Beer's law. If you need a refresher, go back to that those slides. So the ML complex is going to turn into a reddish color. So we are going to have 7 test tubes. We are going to have the concentration of M, the concentration of a tube of M, a tube of L. We are going to have a standard, so a pre-made ML complex reaction tube that has a known concentration. So we are going to measure that absorbance. And then we are going to mix 4 different varied concentrations of M and L to see how much the absorbance differs. And from that, we can figure out how much ML complex was made in solutions 2, 3, 4, and 5 based on what the initial concentration was that we started with. So just a refresher on how to use the spectrophotometer. We want to blank the spectrophotometer with water. We want to add the solutions to the cuvette. But before we do so, we want to make sure that they are rinsed. So after doing the water blanking, we want to make sure that we are rinsing with our solutions, and we are going to add the solution to the cuvette. We want to make sure it's between this little triangle and the sample level here. We want to make sure to wipe it down so that there's no fingerprints or dust that can cause unnecessary absorbance. And then we always want to have like a waste beaker on hand to discard our solutions. And we are not blanking in between solutions. So we want to make sure we're using the same background for each solution. So the very first calculation we are going to be doing is using the standard solution. So the standard solution, we will know what the concentration is. So we know what the C value is. We will also know that our path length is 1 centimeter. So it's always 1 centimeter. And then we will be reading the absorbance of the known concentration. So from that, we can determine what the what epsilon is, or the extinction coefficient of the ML complex. So if you remember from Beer's law, the extinction coefficient is a physical property of a molecule. So the extinction coefficient of the standard solution is going to be a constant that we can use for all of our other different concentrations. Okay, and that is how we will compare all of our unknown ML complex things. Okay, so all right, we did that already. So we will be creating 8 ice tables. So what does that mean? So we have 4 different concentration variations. So tubes 2, 3, 4, and 5 are 4 different variations. So for each variation, we need an ice table for each one. So at the end, for hypothesis 1, we will be calculating 4 different K values, 1 for each tube. So tube 2 we'll do an ice table and K calculation for that. Tube 3 we'll do another ice table and the K calculation for that. Tube 4, ice table calculation for that, and so on. And then we also need to do those same calculations, but for hypothesis 2. And so we will have 4 K values for hypothesis 1, 4 K values for hypothesis 2. So what we're going to do after that is we need to take the average of those K values for K1 and the average of those K values for K2. And then we need to figure out what the standard deviation is for hypothesis 1 and hypothesis 2 based on those K values. And so because K, the equilibrium constant, is a constant, the hypothesis that gives us a K value or K values with the least amount of variance is going to be the correct hypothesis. So the K variance that is closest to 0, the standard deviation that's closest to 0 is going to be our correct hypothesis. And it will be very clear which one is which. So we're not going to be doing we're going to be doing something called a percent variation, which is similar to a standard deviation. It's a type of standard deviation. So we are going to be doing the change in K divided by the average K. So instead of taking the differences between all of the Ks versus their averages divided by the number of trials that we did, like you would in a percent or in a standard deviation, instead we are doing the percent variation. So it's a very simplified version. You're going to take your highest K value, subtract the lowest K value, and then divide that by the average times 100%. And that will give us the percent variation. Okay, so some safety in the lab, we would be wearing gloves and goggles like always. The waste would be disposed in the waste container, and then that waste or in the waste beaker at your bench. And then when you're done with the experiment, you would dump that waste into the waste container in the waste hood. Okay, so this is our long lab report. So what that means is you are writing an entire lab report. So you need to have the title page, abstract, intro, methods, data, discussion, conclusion. So I will refer you all to the lab report writing guide, follow it to a T, and you should be all set. In addition, you need to include the long lab or the questions in the discussion or at the end of your lab report. So let me just go to this one. Okay. So we do have some discussion questions. So what is the most likely stoichiometry of the ligand complex based on your results? So this is something that you should already be answering in your discussion because this is the purpose of our experiment. So you need to decide what the stoichiometry is based on your results and explain why. So when you're writing your discussion, you always have to explain why and point out the data that supports your claims. So in this case, you are going to use the percent variance to back up your claims. Okay. The discussion question number 2, discuss 2 major assumptions. Oh, hold on. Yes, so don't physically add these questions in, just you need to be answering them within your discussion. So discuss 2 major assumptions made in this experiment and how they impact the experiment. So let's go back to Beer's law. Remember that Beer's law is only applicable to concentrations that are within a certain region, right? So Beer's law for when you're making a concentration gradient, you have a linear portion of the data. And then when it gets too concentrated, it starts to plateau off. And the accurate data that you can get is only within that region. So in this experiment, we have to assume that the ML complex concentration is within that linear region. Because if it's not, then we can't use Beer's law. The other major assumption that we are making is that this metal, this unknown metal that we're using, complexes only 1 or 2 ligands. So metals can complex more than that. So if this metal complexed more than 2 ligands, then we would have to do the ICE tables and K calculations for 3, 4, 5, and so on, up to 6 ligands. But we didn't do that. So we're assuming it does 1 or 2. And then again, based on your data, our data is going to say it does one thing. So discuss possible sources of error. So same with the Beer's law experiment. If your cuvette isn't wiped down, if you don't do the blanking properly, if the cuvette has excess liquid in it before you add your concentration, the concentration will be off. There's so many different things that that there can be. If the micropipette isn't calibrated properly, then the volumes we're adding are not what we think they are, things like that. So possible sources of error are always experimental. So calculation is never a source of error because you can always recalculate things. Okay, so does anybody have any questions? Does anybody have any questions? Okay, so we are going to move on to the video. I think Michael does a really good job with this. So let's move forward with that. Okay. And it's not too long, so that's good.
All right. This is the Chemistry 118 demonstration video for the experiment entitled Determination of an Equilibrium Constant. Now, the purpose of this experiment is to determine the equilibrium constant of a chemical reaction in which some unknown metal, M, and an unknown ligand, L, come together to form some metal complex. Now, we don't know the exact stoichiometry of that complex, and therefore we don't know the exact stoichiometry of the chemical equation, but we have 2 different hypotheses. And today we're going to figure out which hypothesis is correct. So, to start the experiment, this is what would actually be done in the lab. In a moment, we will walk through the actual math and a little bit more of the measurements so you have a bit more orientation on how to do that. But this is the experiment itself. So this experiment starts by using Beer's law to determine the concentration of the ML complex that is formed in each test tube that you make. Now, in order to determine the actual relationship in Beer's law that this compound experiences, we will take a standard concentration of the ML complex. So this is a known concentration of our species, and we will measure it in a spectrophotometer. As you can see, it is a slightly red color, it has a slight tinge to it, and it is already deposited into the cuvette. So we make sure the spectrophotometer is set to the right wavelength, it is blank before we do our measurement, and we take our standard and we put it into the machine. Now, most of you, if not all of you, should have experience with doing Beer's law measurements before, so this should be relatively familiar to you. The absorbance that we get here, the absorbance that we get here, we will send to you in a data sheet for you to work with, as well as all of the absorbances we get for the following trials. So with the standard measured, you would make sure the machine's closed, you get the reading, you record it, and you set up for the first trial. Now make sure you clean your cuvette. Make sure it is, if not completely dry, then at least mostly dry, so it doesn't affect your concentration of your next trial. So the next trial consists of creating 4 different test tubes that will vary in the concentrations of the ligand species in each test tube. Now, the reason for this is so we can study how the chemical equation and the stoichiometry affects changing concentrations. But to do that, we keep our metal complex, which is this clear liquid here, sorry, our metal, not the complex, just the metal, in a standard amount of 1,000 microliters. Now, as you can see, before we add the ligand, it is clear. It looks pretty much just like water. Now, when we take our ligand, we'll take 400 microliters of the ligand. This is also a clear substance that looks just like water. Take 400 microliters in a micropipette, and we will deposit it into our metal. As you can see, hopefully, it changed color to that slight red tint that we saw in the standard. Now, because we are doing a standard concentration study, we need to make sure that in each of our test tubes, we have the same concentration, or rather the same volume, so we keep our same concentration of metal. For that purpose, we are going to backfill with water. Now, in this particular example, you can find all of the test tube measurements, so the amounts of liquid that you put in each one, into table 1 in your lab notebook. It's right in the experimental section. Should be right in front of the camera now. For this particular test tube, this is going to be test tube number 2. This is 1,000 microliters of metal, 400 microliters of ligand, and 600 microliters of water. Again, that 600 microliters of water and the 400 microliters of ligand will change. As long as they come out to 1,000 microliters, we're okay. Now, once this is mixed, once this is ready, we take this and we deposit it into our cuvette. Make sure there is enough to measure. Take the cuvette, and insert it in the spectrophotometer. You take a measurement. And once we take the measurement, we will record a data set for you and send it to you so you can do the rest of the math and do the lab report for this experiment. We will send you 4 different test tube absorbances, and you will do your math from there. Okay, so after doing our measurements, I'm now going to walk through an example for most of the calculations you're going to have to do for this experiment, as well as an example for filling in your data tables. Now, we're using numbers that we got here. These are not necessarily the numbers that are going to be given to you to do your experiment with. So the first one to note is that for our measurement of the standard absorbance, so the known concentration of our MLX complex, we're going to be using 0.223. This may be different in the data you are sent. Please make sure you use the correct number, the number that you are sent in your calculations. So how does this start? So we know Beer's law is this equation. Absorbance is equal to the molar extinction coefficient times the path length, B, times the concentration, C. Now, in all of our machines, we know the path length is 1. And because we're working with a known standard, we know the concentration. In this case, for our MLX complex, that concentration is 0.0680 millimolar. Now, we measured an absorbance of 0.223. The first thing we need to do is understand how much light this chemical will absorb per unit of concentration, so we can understand what concentration we get for each following trial. The way we do that is we determine our epsilon. So if we rearrange Beer's law to solve for epsilon, we get epsilon is equal to the absorbance divided by 1 times concentration. Filling that in here, we have our absorbance, our path length B1, our concentration of our standard 0.068. When we do this math, our epsilons, the epsilon for this example, comes out to 3.279. Now, again, you may not get this exact number. It all depends on the data you are sent. So when we move to our actual trials, in our first test tube, we have a total volume of 2,000 microliters, a volume of our metal bonded to some ionic compound that it will break away from. We used 1,000 microliters of that, and we put in 400 microliters of our ligand. So the first thing we need to do is we need to calculate our formal concentrations of both the metal and the ligand. So the way we do that is we use our good old friend M1V1 is equal to M2V2. In this case, if we're trying to find the metal concentration, then we know our initial concentration of the metal is given as 2.04 millimolar. You can find this in your table. And we know that we used 1,000 microliters of this solution. So M1 will be 2.04 millimolar, V1 will be 1,000 microliters. Now, all of our test tubes wound up with the same final volume of 2,000 microliters, so we know our V2 will always be 2,000. Now, that means we need to solve for our M2 value, this guy here. That is the concentration of our metal solution in the test tube before any reaction takes place. Now, the way we do that is we rearrange our M1V1 is equal to M2V2 into M2 is equal to M1V1 divided by V2. We fill in the numbers that we have from above, so our M1, our V1, and our V2. And the concentration of our metal in this test tube comes out to 1.02 millimolar. We go back, we fill that into our table. Next, we calculate in the same fashion the formal concentration of our ligand species in the same test tube. Now, for the metal between each test tube, the concentration should not change. We do not change the amount of metal we put in each test tube, and therefore the concentration at the end will stay the same. Our ligand, however, does vary. So this concentration is only going to be correct for test tube number 2. You will need to do successive calculations for test tubes 3 and 4 and I believe 5. Now, the way you calculate the formal concentration for the ligand is the same way as we demonstrated for the formal concentration of M. You just have to change your M1 and your V1 to correspond to the M1 2.01 millimolar for the ligand and the V1 that you use in each particular test tube. For test tube 2, when you do the math, we came out with 0.42 millimolar. Now, this number is the absorbance that that test tube gave. This will be given to you. This is something we will send to you. This example here may not be the one that we send, so please take note. This number and the following calculations may change for you very slightly, but this is how you do it. Now, once you have the absorbance, we know our epsilon from our standard, so we can calculate our mLx concentration in the test tube. The way we do that is we return to our Beer's law. We rearrange Beer's law to solve for concentration C. And to do that, we have absorbance divided by our molar extinction coefficient, epsilon, that we determined earlier, times B, our path length. Filling in our numbers, if we use an absorbance of 0.218, we divide by our molar extinction coefficient of 3.279, and we multiply that extinction coefficient times the path length of 1. We come out with a concentration of our metal in this test tube as 0.0665 millimolar. Again, because your absorbance may be different, this concentration may be different. Please make sure you use the one that we sent you and not the one from this video. So, returning to our table, we fill in 0.0665 millimolar. Next, in these 3 cells, all of which you can find in your worksheet, as well as this entire table, you just convert from millimolar to molar concentrations. Now, hopefully you have a lot of experience at this point. you just simply divide your millimolar concentrations by 1,000, and you will get your formal concentrations in molarity. Now, once you have this for each test tube, all 4 trials, you're ready to move on to calculating the equilibrium constant in each test tube. So to do that, we have to understand the ice tables and the math behind the ice tables that go on in each test tube. So when we start each reaction, what we are looking for is the change in the concentrations between what we put in and what we get out for the metal, our ligand, and our metal ligand complex, which is our product. So these 2 are reactants, this is our product. Because we have 2 different hypotheses, you'll have to do this twice for each test tube. This example up on the board right here corresponds to hypothesis 1 here, which says that there is a 1-to-1 ratio of metal to ligand to form metal ligand complex. Now, when we do this, and we're trying to solve for our concentrations, remember that we need our ice table. So to start with our ice table, we start with what we know. So the initial concentrations of each chemical. For that, that will be our formal concentrations. So for M, formal concentration of M. For the ligand, formal concentration of the ligand. Now, because we say this is before the reaction happened, we set our product concentration to be equal to 0. Next, we figure out the change that each concentration will experience as the reaction proceeds. Now, because we know the final concentration of our metal ligand complex, we know that the end value, the change that the metal ligand complex will experience during the experiment, will be equal to that end value. So we go from 0, it experiences an increase to the final concentration that we calculated using Beer's law. And so you add the concentration of the metal ligand complex. So now that we know that, we know that each of the 2 reactants, both M and L, will experience a 1-to-1 ratio in order to make product. Now, because we are making product, that means for every 1 product made, we lose 1 L and 1 M. So the change that both of these concentrations experience will be equal to the negative value of the concentration of our product. So when you go to calculate the values of the concentrations at equilibrium, you do for M, our initial value, which is the formal concentration, minus the change it experiences, which is the concentration of ML complex, so formal minus ML. For L, it's the same. The formal concentration of L is how you start. The formation of the metal ligand complex decrements the value. And so it is the formal concentration of L minus the concentration of the metal ligand complex. And for the product, the metal ligand complex, it simply goes from 0 to the value that you calculated in your table. Now, what does this actually look like for our numbers? If we start with initial formal concentration of M of 1.02 times 10 to the negative 3 in molarity, not millimoles, molarity, and we produce 6.65 times 10 to the negative 5th molarity of metal ligand complex, then you simply do 1.02 times 10 to the negative 3 minus 6.65 times 10 to the negative 5th, and you come out with 9.54 times 10 to the negative 4 molarity of your metal at the end of the experiment in test tube 2. Now, you do the same procedure for your ligand, you do the same procedure for your product metal complex. These 3 values, these equilibrium values, will go into the table for hypothesis 1 located at the end of your lab notebook. Now, they will be oriented slightly differently. They will be oriented with a vertical orientation, so it will be M, L, and then the complex. It's these values here. Don't get too confused. Now, the problem comes when you switch to hypothesis 2. All of this math up here is based off of the idea that there is a 1-to-1 relationship between our metal and our ligand and our complex. Hypothesis 2 says that it is possible for the metal and the ligand to have a 1-to-2 ratio, and therefore the ligand will have a 2-to-1 ratio with its product. In other words, you take one M, you stick two L's on it, and you form the Ml2 complex. So when you go to do the math for hypothesis 2, you can use the same template, but you have to be aware when you go to the actual chemical equation, that 2 in the metal in the ligand will show up here. If the marker will work, will show up here as a 2 and here as a 2. You will multiply the concentration of complex by 2 to represent the fact that 2 ligand atoms, molecules, whichever it is in this instance, are being consumed to form the complex. Now, you do this again, and you do hypothesis 1 and hypothesis 2 for each test tube. At the end, you will need to calculate the equilibrium constant for each test tube. Okay, so once you're done with your ICE tables and you filled out table 2 and table 3, the last part of those tables is to calculate your equilibrium constant K. Now, for each hypothesis, this is going to be slightly different. Hypothesis 1 is slightly simpler. Because we have a 1-to-1 ratio of our metal to ligand and a 1-to-1 ratio of our reactants products, so 1 metal, 1 ligand, 1 complex, our K value is simply going to be our products divided by our reactants. So concentration of Ml divided by concentrations of M and L. All of these are going to be your equilibrium concentrations. So you can do it simply from the math that you fill in the tables. For hypothesis 2, your equilibrium constant is going to be slightly different. Because we have the metal coming together with 2 ligands to form an Ml2 complex, we have to alter our reactant concentrations very slightly. So the Ml complex concentration is still what you got from the table. The M and L concentrations are still what you got from the table. These values don't change. What does change is when you do the math, you have to square the value of your ligand concentration. This is to account for that 2-to-1 ratio of the metal to ligand. So once you have that, you will have 4 K1s, so 4 K values, 1 for each test tube, according to hypothesis 1. And you will have an additional 4 K2 values, 1 for each test tube, according to hypothesis 2. The way in which we're going to determine today which of these chemical equations is correct is by using the percent variation. Now, the way percent variation works is that it is a mathematical way of calculating how much does my answer change between successive tries. Because we're trying to calculate an equilibrium constant, it should be as constant as possible. So this, whichever hypothesis leads to the smaller percent variation will be our correct answer. The way we calculate percent variation is we take the average of our K values. So we have 4 K1s, so we'll average them together. And we take what's called the delta in these K values. Now, the delta is essentially the range, if you remember that from statistics. So what you do is you take your largest K1 value and you subtract your smallest K1 value, and that will get you delta K. You then divide by the average of your K1s and multiply by 100, and that will be your percent variation. Hopefully, this is really, really small. For K2, it's the exact same formula. You take the average of your K2s and you plug it into your denominator. You take the largest K2 and subtract the smallest K2 to get your delta K. You divide them, multiply 100, and you get another percent variation. Hopefully, this is also very, very small. Now, whichever one is bigger is your incorrect answer, and whichever one is smaller is your correct answer.
All right. All right. Oh my gosh. All right. So does anybody have any questions about the lab? So All of the YouTube links, Alejandra, and everybody, those are on the course library page. So why don't I show you guys how to find those? So if we go to Blackboard, so I obviously have a million courses, but the course library for me is down here. So the Chem 118 course library summer 2021. If you go to course materials and down here, videos of experiments. All of the video YouTube links are here. So today's is the equilibrium constant determination. So you would just use that. Okay. Does anybody have any other questions about this lab? Okay, so this is the data that is in the data folder. So we have our measured absorbance of our standard. So ours is 0.221. So like Michael said, it's a little bit different, but we have the same concentration here. So it really doesn't vary very much. So from that, you are going to have to figure out what epsilon is. So the molar extinction coefficient. Again, just like Michael said, the concentration in millimolar for FM is going to be the same for all of the trials. FL, you will have to calculate. So for tube 2, the FM and FL values are the same as what Michael had. And then based on the epsilon value and the absorbance that you're given, you need to solve for the ml concentration for all of these tubes, and then convert them to millimolar. So then you're going to do all of the ICE tables. So in the in here you are given the ICE tables here. So they look a little bit differently. Like Michael said, they're vertically shaped. So you don't have to put the ICE tables this way if you would prefer to have them in the same orientation that Michael had in the video. You can do that instead. So in your lab report, that depends. If you are going to do the ICE tables in this formation, then you just need tables 2 and tables 3, or you just need these tables. However, for instance, let me show you the sample data that I have prepared. In my Excel, I prepared ICE tables in the traditional way. So if I was to present this data in a lab report, I would need to set it up like this, in which case I would probably have about 1, 2, 8, like 10 tables. So so that totally depends on what you would prefer. I prefer to look at it like this. I think it's easier, but you are more than welcome to use just these 2 little tables here. Yeah, okay, so what calculations are needed in the report? So anytime you do a certain type of calculation, you need to include that. So you're going to need an example of Beer's law, so using Beer's law. So I would recommend just the first one to solve for epsilon. You will need an example of the ICE table calculations for both hypotheses. So you can choose, so I would choose the L calculation. So you want to do the L calculation. You can just choose one of the test tubes. So maybe test tube 2, you want to show the M calculation for for hypothesis 1 and 2, which is the same. And then you will need the L calculation for hypothesis 1 and an L calculation for hypothesis 2. You will need sample calculations for the K for hypothesis 1. You will need an example of a K calculation for hypothesis 2. And then it asks for standard deviation, so you don't have to show a standard deviation calculation. Actually, it should say range of K. So in the makeup data, I don't know why they have standard deviation here. But what we need is the range of K. So show a range of K calculation and then percent variation calculation. So you don't need to do one for each hypothesis because those calculations are going to be the same. So does that make sense for that? Yes, you will have access to this recording after lab today, so it will take some time to process. Yes, so good question. So it doesn't really matter what you call the test tubes. If you call them test tube 1, 2, 3, 4, just make sure to be consistent when you're talking about them. So for instance, in the procedure in the sample data, it said to have a standard test tube and then label the other ones 2, 3, 4, and 5. For some reason, it then numbers them 1, 2, 3, 4, which is strange. It should label them 2, 3, 4, and 5. But if you consistently, so in your methods section, if you said you labeled the tubes 2, 3, 4, and 5, in your tables, it should also say 2, 3, 4, and 5. Does that make sense? Okay, awesome. So B is path length. Path length is 1 centimeter. So the path length is the distance that the light travels through the tube. So all of the cuvettes are 1 centimeter in length. That is a standard. Okay. Any other questions? Any other clarifications you guys need? Okay, so I'm not going to break you guys into breakout rooms because you guys so far have like all needed me at once, and that's really crazy. So so any clarification I do when somebody asks a question, I think it's better for the whole class to hear it. So the due dates for this, sorry, I always forget because I teach on Wednesdays and Tuesdays. So let me just double check. Which one are you guys? B1. Okay, so today is Wednesday, so your lab report is due Saturday at midnight. So, so because this is the long lab report, this is a rough draft, but you need to treat it as a final draft of the lab report. So, so once we grade this, you will get a grade for it as you normally would. And then based on the feedback that we give you, you need to make those changes for your final lab report grade. So the final lab is worth some extra points. So if you don't make any changes and resubmit the same thing, you'll get a 0. So it's based on whether or not you made the changes that we told you to make. So somebody might have like 9 changes to make. And so their grade will be divided by those 9 changes. Somebody else might only have like 3 or 4 to make, and their grade will be divided by those changes that they need to make. So a lot of the grading we do, we will make comments on things, even though we don't take points off for it. If we comment on it and suggest you make that change, whether or not you originally got points off for that thing, you still need to make that change for the final. Okay. Does that make sense to everybody? So the final lab report due, I'll make sure that the submission dates make sense to everybody. So the final lab report due will be due a week after you submit. So I will double check on the final lab report. So in between, we will also need time to grade your draft. So there will be a period of time from when you get the feedback so that you can update those changes. So the changes are usually pretty quick to do. Okay, any other questions? Yes, so in the sample data, if you look at the screen, you are given the standard concentration and the absorbance. So you will use that data. So this sample data is also found on the course library page, and I believe Victoria has also put it on our page. So sample data for lab reports, that will be equilibrium here. So it's all here for you. Yep. Alrighty. So I will be here until 3:30 as always. So if you have any questions, feel free to ask. Before you leave today, I will need to make sure that you are confident that your data is correct. We'll compare your data to mine, and if it's matching and you don't have any questions, then you're free to leave. Okay, and don't forget about your post-lab summary as well.